Hello and welcome to yet another lecture on basic electrical engineering. Myself, Prathita Roy, Assistant Professor of Dr. Sudhir Chandra Degree Engineering College, Electrical Engineering Department. So till now we have learned about the KCL, KVL, nodal analysis, loop analysis, mesh analysis, and also the source transformation along with Thevenin's theorem. How to approach to a solution of a particular circuit using the conception of Thevenin's theorem. So today we will do the Norton's theorem and how we can able to provide a solution of a particular circuit using the help of Norton's theorem. So the Norton's theorem states that any two-terminal active network containing voltage sources and resistance, when viewed from its output terminals, is equivalent to a constant current source and an internal parallel resistance. The constant current source, known as Norton's equivalent current source, is of the magnitude of the short circuit current at the terminals. The internal resistance is the equivalent resistance of the network looking back into the terminals and with all the sources replaced by their internal resistance. So the first step is that we have to find for the particular circuit we have to find the IN, that is the Norton current. Means the problem is that we have to find the current that is flowing through the RL resistance, RL. So we have to short circuit that resistance. In case of the Thevenin's, we open circuited that, but in case of the Norton, we must short circuited the resistance at which we have to find the current. If it is short circuited, means these two are connected in parallel, the R2 will be short circuited. So I of SC will be E by R1. That is the Norton current. Then the second thing is same, that we have all the internal sources that we must be omit. Means if there is a voltage source, it will be short circuited. If there is a current source, it will be open circuited. Means the voltage source is short circuited. We have to view from there and we have to find the equivalent resistance, that R1 and R2 are in parallel connection. Then the third step is that this Rn will be connected in parallel with the In or the Isc. And the fourth step is that we have to connect the RL across the AB terminals in order to find the current that is flowing through the RL. So how we can able to, the procedure is that the calculate the short circuit current IN at the network terminals, redraw the network with each source replaced by its internal resistance, calculate the resistance Rn of the redrawn network as seen from the output terminals, draw the Norton's equivalent circuit. So we can see the Norton's theorem with the help of an example. So let's start. Norton's theorem with the help of an example. Norton's theorem with the help of an example. So let us, our problem is that we have to find the current. Let us take a circuit, the example. First of all, we are drawing the circuit in order to approach to a Norton's problem. So let's take this is the 10 volt. This is 2 ohm. This is 2 ohm. And this is called the RL equal to 4 ohm. RL equal to 4 ohm. So we have to find the load resistance, load current IL. We have to find the IL, that is the current that is flowing through. We have to find the value of IL, that is the current that is flowing through RL, the load resistance, with the help of Norton's theorem. We have to find the value. What is the value of RL with the help of IL, that is current flowing through the RL with the help of Norton's theorem. So, just approaching to the first step, that is called step 1. So our first step suggests that in case of the Thevenin's theorem, we just open circuited the terminal. So this is the AB terminal. We have open circuited that AB terminal in order to find the VTH or VOC. In this case, the resistance through which the current we have to measure with the help of Norton's theorem. We have to first short circuited that resistance, means first RL should be short circuited. Short circuited this RL. And then we have to measure the value of IN, that is called the short circuit current, or say called I of SC, the Norton current. We have to measure that. This thing we have to measure first. First step is to short circuit the L, through which that we have to measure the value of I of RL. So how we will approach? This is our 10 volt, 2 ohm. This is our 10 volt. This is our 2 ohms. And this is our 2 ohms. So what we have done? We have short circuited that particular terminal, means that RL. We just short circuited it and we have to find the IN or ISC through that RL. We have to find that, means the AB terminal is short circuited. So we have seen that if I go through this diagram, the current that is flowing from 10 volt, it is divided here into two parts. This part and this part, means these two are connected in parallel. This short circuited part and this 2 ohm is connected in parallel. So if the two resistance is connected in parallel and one is short circuited, means the parallel one is also short circuited. So this one is also be short circuited. Okay, if these two resistors are connected in parallel and one is short circuited, means the total equivalent resistance will be short circuited. Okay, so now we just remove that particular thing. The equivalent resistance become this one. Okay, so the equivalent resistance become this one. Now the equivalent resistance become an AB terminal become this one. So what is the value of IN? IN is V by R, means, and so IN is V by R. IN is V by R. So the equivalent resistance become this one. All are short circuited. Okay. So the equivalent resistance become IN equal to total V by R. So here R is 2. So 10 minus 0 by 2. So the IN that or ISC that is become 5 ampere. That is the value of IN or ISC that we have obtained from the first step of the Norton. Is IN or ISC, that is become 5 ampere. That is become 5 ampere. So this is our step 1. So short circuited that the particular resistance through which the current is flowing, and then find the value of the ISC or IN. So let us take the approach to the step 2. So let us take the approach that is given that the fourth step that we are calculating, the first step that we have calculated. And let us take the approach to the step 2. So step 2 suggested that we have to find the Rn or the Norton resistance, that is called the R equivalent resistance, keeping all the internal sources deactive. Means if there is a voltage source that we have done in case of the Thevenin's too, that the voltage source is short circuited and the current source will be open circuited. Okay, just we have time to do that. The voltage source is short circuited and the current source is open circuited. We have to do that particular thing. So let us take the approach to the step 2. There is a voltage source that is short circuited. Means this part is the voltage source 10 volt is short circuited. Okay, and followed by that 2 ohm. There is a 2 ohm there. There is another 2 ohm is there. So this is our step 2. This is our step 2. So here, this is the open circuited part. From here we have to see that the value means we have 2. This is another 2 ohm. So we have to keep our eye on that particular part that we have done in case of the, we have to keep our eye on that particular part and view from that particular part. The step 2 is there in order to find the step 2 will be there in order to find the value of Rn or R equivalent. Rn or R equivalent. We have to find the value of Rn or I R equivalent. Value that Req that we have to find. So means the same process we are considering. There is an imaginary voltage source is there. This is a positive and this is a negative half of the voltage source, and the current is starting to flow from there. And see, the current is divided into two parts. When you reach that particular point, it is divided into two parts. This current is divided into two parts. When they reach at that particular point, this point, it is divided into two parts. And then they are adding here and coming back with the same current. So the current is divided means these 2 ohm and 2 ohms are connected in parallel. So the R equivalent became, or the Rn became, the parallel connection of 2 parallel with 2 means the 2 into 2, 2 into 2 by 2 plus 2. That is R equivalent became 1 ohm, or Rn or the R equivalent became 1 ohm. Okay, this is our step 2, that the R equivalent or the Rn became 1 ohm. So now we will approach to the third step. Now we will approach to the step 3. The step 3 suggests that the step 3 that is given here, it is suggests that the we have to connect that In and the R equivalent in parallel. We have to connect that In and Rn in parallel. That means our step 3 suggests that our step 3 that is suggested that we have to, our step 3 that is suggested that we have to connect it, the In and that R equivalent or Rn in parallel. These two must be connected in parallel. Okay, so this is the In that is given to us. This is the IN that is given to us, our ISC, that is 5 ampere, and along with RL, or the RN, that is R equivalent, or RN, that is we have found, is given as 1 ampere, and this must be connected in parallel. Followed by our third step is that we have to connect that particular resistance through which we have to measure the value of current with the help of Norton's theorem must be connected in parallel with the RL. This is called the RL, and RL, that is the 4 ohm. So our step is that IN and the RN, that is being connected in parallel, followed by the resistance RL, through which we have to measure the current will be connected in parallel with the RN. That is our third step. So now followed by our fourth step. Our fourth step is given that we have to find the value of current through the RL, that is IL, with the help of the Norton's theorem. So IL will be that this 5 ohm is divided into the two parts. So these two are in parallel, 1 ohm and the 4 ohm. And the rules to connect the find the current through a parallel resistance, say through the RL. So IL means the current through the RL will be the total current, that is the 5 ampere, and it is the resistance at the opposite arm of the RL, that is 1 ampere, divided by the summations of the two resistance, that is 1 plus 4. Total current multiplied by the current in the opposite, the value of the opposite resistance, means the value of the resistance opposite to a parallel connection opposite to the RL, that is RN, that is 1 ohm, and followed by the summation of the two currents, that is summation of the two resistance, 5 by 5 equal to 1 ampere. So with the help of the Norton's theorem, we have find that the current through the RL will be, or the IL will be the 1 ampere with the help of the Norton's theorem. The current that is flying through the RL will be the 1 ampere with the help of Norton's theorem. Now let us check it with the help. Now check this answer is correct or not. So this is the particular resistance. This is the particular circuit. So this current is coming from here. It is divided into two parts. So the equivalent resistance is that for that particular circuit is that this 2 and 4 are in parallel. So 2 and 4 are in parallel, followed by the 2 ohm that is connected in series. Okay. So total resistance will be 2 plus 2 into 4 plus 2 plus 4, that is 6. The total resistance will be there. The R equivalent value will be there after calculating is that 10 by 3 ohm. 10 by 3 ohm. So what is the current? The current that is flowing through the circuit is 10 by V by R, that is 10 by 3, means the current that is flowing through that will be 3 ampere. I am just cross checking that this answer is correct to the Norton or not. So if the total current is 3 ampere, the 3 ampere current that is flowing through here, it has not divided into the two parts, 2 ohm and the 4 ohm. So what is the value of IL? The value of IL will be the same formula that we have used, that the total current I, current through the opposite ohm, that we have to find the current through the 4 ohm. So means the 2 followed by 2 plus 4. So it will give that it will be 6 by 6, that is 1 ampere. So this answer is equivalent to this answer. So by the cross checking, we are saying that the Norton's the answer that is get for the both Norton's, for the simplification of the circuit and along with the Norton's theorem are same, that is 1 ampere. So today we'll learn about the Norton's theorem and how we can able to approach to a particular circuit with the help of Norton's theorem. That we have already done. We have to cross check that and we see the both in case the answer is right. So with the help of the Norton's theorem, today we will able to learn how we can easily approach to a particular solution of a circuit with the help of Norton's theorem, or a solution to a circuit with the help of Norton's theorem. Thank you.